transmitiendo. ¿Vale? El aire...
Correcto. No. Están en orden. Están en orden, pero multiverse va entre medio.
Ah, vale.
Al principio,
Este es el orden oficial,
sí,
vale.
pero este es mi móvil.
Hago
¿Me
una,
puedes
bueno,
hacer
hago una
una...?
foto.
Da igual, en realidad.
Es igual, ¿no?
No, yo porque diga uno. Ya no lo tienes que pensar.
Vale.
Pero da igual, ellos no creo ni que lo sepan.
No.
Se lo dijimos, pero creo que
Vale, vale.
Vale. Y multiverse es que lo tiene que...
Vale, que es el segundo.
Pero pues... Pero, ya podemos...
Vale, pero bueno, ya me ayudaréis a hacer el cambio.
Sí, vamos a esperar. A ver.
¿Cómo?
Ahora.
We're gonna wait a couple of minutes and we'll start. Okay, thank you so much. We will be starting. This is an industry-focused session where we have invited 6 companies that are currently working on quantum technologies. So first of all, thank you so much for coming. It's an honor to have you here. We have GMV, Multiverse Computing, DDDA, Das Photonics, Repsol, and Kilimanjaro. And with this session, basically, they will be doing an introduction to what they do, their projects, their company, about 10 minutes, and then we will open the floor for questions. So if you have any question on what they do, anything, it's the time to ask them. So we will start with Das Photonics with Alberto Martinez. So please welcome him. Vale. Ahí.
aquí si quieres y...
Bueno, me puedo quedar aquí. ¿Funciona? Sí. Hello, my name is Alberto Martinez, and I will show you the work that Das Photonics has been making in Cuco, as well as the quantum technologies that we have been implementing in our products. Das Photonics is a company founded in 2005, focused on the implementation of photonic technology in order to create products for defense, avionics, and space. We implement photonic technology instead of electronic technology because photonic technology has a bigger instantaneous bandwidth, is more efficient for both energy and time consume, and is more resistant to noise and interference from the signals that we analyze. We developed from photonic integrated circuits to whole instruments and applications for defense, avionics, and space that we sell to customers such as Airbus and Boeing, for example, for defense and avionics, and the European Space Agency in the field of space. We have an autonomous research area in Das Photonics, which researches those key technologies that we believe will be important for our company in the next years. For example, the three first projects that appear in the first row are projects where we are researching metasurfaces, which will be a key technology for defense applications. The first project in the second row, Disrupt, is a project where we are researching photonic instruments for biomedicine. And the two last projects, Cuco and Inspire, are the projects where we are researching quantum technologies. In Cuco, we are researching quantum computing, and in Inspire, we are researching both quantum computing and quantum magnetometers for UAVs. We also have a project in development where we have implemented quantum technology, Project QTYR24, where we are implementing quantum key distribution for quantum communications between a satellite and ground control. Das Photonics is developing the photonic instruments that we will use to generate the single photon state, emitting it and receiving it in the satellite. In Project Cuco, the different partners are researching the advantages of quantum technology for key areas of Spanish industry. In our case, our goal is to study if there is any quantum advantages to quantum computation in the field of signal intelligence. We want to study if there is any quantum advantage for the classification of interpulse and intrapulse modulations for radar signals and the prediction of frequency hopping spectrum signals. Signal intelligence is the gathering of information from electromagnetic signals. An electromagnetic signal is made of the union of a carrier signal, which is unmodulated and just gives the frequency of the radar signal, and the modulated signal, which is modulated and has the information that carries the radar signal. There's two modulations inside the carrier signal, the modulated signal, the intrapulse modulation, which is the behavior of the signal inside one pulse, and the interpulse modulation, which is the temporal space separation between two consecutive pulses. We want to determine both modulations in order to characterize the signal and extract information from it. Until recently, companies in the field, like Das Photonics, have used heuristic algorithms in order to characterize the signal. However, heuristic algorithms are known by being quite inefficient and time-consuming. That's why recently, in Das Photonics and several companies in the sector are researching and investing in artificial intelligence in order to substitute those heuristic algorithms because they are more efficient and less time-consuming. For example, for interpulse classification, since the data is expressed as a temporal series, we are researching recurrent neural networks in order to do the classification. We are also trying to do the classification with K-means, KNN machine learning algorithms. For intrapulse classification, the data is expressed as spectrographs. Since an spectrograph, spectrograph can be understood as an image, we are using convolutional neural networks for its classification because those are the networks that perform best for image classification. And for frequency hopping speed spectrum, since the data can be expressed both as temporal series and spectrograms, we are using both recurrent neural networks and convolutional ones for classification. As we know, quantum computing can outperform classical computing in several applications. That's why in DAS Photonics, our goal for Project Cuckoo is to determine if there is any quantum advantage to the use of quantum algorithms instead of classical algorithms for artificial intelligence, quantum machine learning and quantum deep learning in these applications. We have started with quantum machine learning, trying to implement a quantum version of K-means and KNN algorithm. In the literature, we can find several implementations of quantum K-means algorithms, but not for quantum KNN algorithms. That's why in DAS Photonic, with the theoretical knowledge of the quantum K-means implementation, we have implemented our own version of quantum KNN algorithm. Both models are based on a quantum distance algorithm. This algorithm codifies two samples and operates on the quantum state in order to generate a probability that is related to the distance between those two samples in the Hilbert space where the quantum state is defined. For the quantum K-means algorithm, that probability is transformed into a distance, and we use that distance in the classical algorithm for clusterization. In the quantum KNN algorithm, we translate that probability, which was related to distance, to a probability that is the probability of assigning correctly a label to the sample that we want to classify. We have trained both algorithms with a simple dataset and the interpulse dataset. And in each case, we have achieved an accuracy that is similar to the classical one with the classical K-means and KNN algorithms. Furthermore, we have obtained a quantum advantage in the form of parallelization of the calculus thanks to quantum state superposition. We have also studied quantum deep learning, where the literature shows several implementations for the different architectures that we want to implement. All these implementations show that quantum deep learning offers simple algorithms with fewer weights when compared to the classical neural networks. There are two strategies in order to implement these quantum neural networks. The first strategy uses a generic circuit which tries to emulate the classical one, and each part tries to emulate a part of the classical neural network. For example, for a quantum convolutional neural network, there's a part of the circuit which tries to emulate the kernel used in a classical convolution. These models with this strategy are simpler to implement, they are less complex, and probably will be the first that we will see in a quantum computer. However, they are not guaranteed to work properly after training because they are generic circuits, and therefore they can fail pretty easy. The second strategy is to define an equivalent to a classical neuron, a quantum neuron. For example, there's a circuit with one of the proposals that there is in the literature, and from there, implement a circuit that is the same as the classical one, but substituting the classical neurons for quantum ones. These models are guaranteed to succeed because they have a quantum neuron and they follow the architecture of a classical neural network that we know that it works, but are more complex and usually they don't train properly. That's their main drawback. After talking about the different strategies, first we are going to talk about the quantum convolutional neural network for intrapulse classification. We have used the first strategy where the circuit that appears in the superior part of the slide is the kernel that we have used, the circuit that will try to emulate a kernel. We have implemented a model that can classify up to 4 categories at the same time. And we have trained it with both simple datasets and a simplified intrapulse dataset. And we have obtained an accuracy that is similar and in some cases even greater than the classical convolutional neural network. However, there's still room for improvement because this model can be scaled up pretty easily. That's why we're working right now. Second, for the quantum recurrent neural network used for interpulse classification, we have used the second strategy, defining the quantum neuron that appeared in the previous slide. And using an an architecture equal to the classical recurrent neural network. Since this model follows the second strategy, we are still working on implementing the model and training it properly because we are finding some problems with the training. And finally, for the quantum long-term memory used for both interpulse classification and frequency hopping prediction, we have used the first approach using an architecture that is equal to the classical one, but swapping the classical gates of a long-term memory for variational quantum circuits. We have trained the model with simpler datasets, the interpulse dataset and the frequency hopping prediction dataset, and in all cases, we have obtained an accuracy that is equal or even greater to the classical LSTM, with the quantum advantage of the simplicity of the model and the reduced number of weights. As with the quantum convolutional neural network, the QLSTM can be scaled up, and we believe that we will be able to even classify and solve problems that are more complex than the one that we have tried for now. As a conclusion, in Das Photonics, we have been studying quantum machine learning and quantum deep learning for classification and prediction of the problems that I have defined. We have achieved accuracies that are equal or similar to the ones that can be achieved with classical models with quantum advantage, either with parallelization or with the simplicity of the model. However, there are a couple of disadvantages that we have to take into account, like the dependence of the results with the codification of the data, or the limitations that quantum hardware has, and we have to take into account when designing and implementing quantum circuits. However, we are adamant that when quantum computers have a breakthrough and we are able to implement even more complex circuits, we will be seeing quantum deep learning and quantum machine learning as a viable way to solve these classification and prediction models. Thank you for attention, and if you have any question.
Thank you so much. Somebody has any question? No, I have one question. So these algorithms that you described, do you use it for your own applications, or it's because you have clients that have these kind of problems and you're trying to develop for them?
In this case, in Cuco, the algorithms that we have chosen have been chosen just because they are quantum implementations of classical algorithms. We didn't have any requirement, neither from Cuco nor for any client, because
like research.
This research is for us.
Okay. So, thank you so much. Any other question? No? And thank you so much. So the next person will be Robert Farzan from GMV. Thank you, Robert.
Okay. Hello, I'm Robert, and today I'm going to be representing GMV this session about quantum computing, summarizing some of the main achievements in the Cuco project. But first, let's get into context of who are we, GMV. We're a multinational group. We were founded in 1994 from the Universidad Politécnica de Madrid. That was mainly focused on aeronautics and space. That's the Grupo de Mecánica de Vuelo. That's the acronym for GMV. But we've evolved to be much more than that. We have now some defense and security, transportation systems, and now we're into AI and also quantum computing, healthcare, and other fields. We are very spread around the world. I think we're more than 3,300 employees right now in more than 10 countries. And we have a very big portfolio of clients, including banking, the European Space Agency, which is a great client of ours, public institutions here in Spain and European, and so much more. But let's get to the cool part. Not that talking about GMV is not cool, right? But I don't want to get fired. But what quantum projects in the scope of R&D we have on GMV? Well, we're working on Cuco right now that ends this year. We're also collaborating in Quantum Spain. We have also very interesting projects in quantum key distribution and a big project, Quantico, with the European Space Agency. Now I'd like to share with you some of the most remarkable achievements in our Kuko project that we divided in 3 main use cases that are oriented to GMV interests in Earth observation and this kind of application to the industry. The first use case is about photovoltaic panels. It's a very simple problem in the scope of the classical solution because it's already resolved many years ago, which is just classifying an image, a satellite image, based on if there's presence or absence of panels in these solar panels in this satellite image, and if so, do a semantic segmentation, binary semantic segmentation on this image to highlight the exact region where the panels are located. But from a quantum machine learning based approach, this problem is much more difficult than the classical one. All right. The 2 main challenges are quantum encoding and then selecting the most suitable learning architecture for it. On the quantum encoding part, we really hit a big wall at the start of the project because we figure out that directly encoding images in current quantum circuits, it's almost unfeasible because it requires a lot of number of qubits and the depth of the circuits are impractical on this FRQI or any QR forms of encoding. So we really figure out that we have to go for the hybrid architectures, doing some dimensionality reduction of the images or other techniques that allows us to reduce the data so we can embed it into the quantum circuits. Then on the learning part, we've explored a lot of architectures, including variational quantum classifiers, also quantum kernel methods, also called QSVMs, because we like to put the Q in before every word, but sometimes it's not the most appropriate approach. And this approach is about just taking a feature map and its conjugate transpose, and you compute the distance metric or the similarity between every pair of points in the dataset, and then you build this kernel matrix that you use in the SVM, then to classically optimize the SVM to do a classification problem, which resulted in very good results, very near to the classical ones. And in semantic segmentation, it was a much more complicated problem because of, as in Das Photonics, they said about quantum deep learning, these are big architectures with millions of parameters, and some things embedding this variational quantum classifier is not as easy, mostly because the number of parameters of the classifier in the quantum part are very few in comparison with the number of classical parameters. So the influence is not that visible in many cases. We tried this architecture both with discrete variable and continuous variable, and these are some of the cool results here. We have in the first the image, the second the ground truth mask of the image, and the third one is our continuous variable classificator. Well, it's a binary classification based on pixels, so yeah, the semantic segmentation model. And then we also take an approach on Q-means or QK-means, quantum K-means, with two implementation on swap test and flip-flop QRAM to do pixel-wise classification of each pixel in the mask. That's what you see there in blue and red dots, and it doesn't retrieve the best results. But it's an interesting approach to try at least. Some of the conclusions here are that hybrid approaches are almost inevitable in these cases, and that we have to reduce the data in the case of high dimensional data that like images with multiple channels, a very large number of pixels, and training on real hardware is almost infeasible also because Q times the costs and the time. On the second use case about mission planning, it's more focused on optimization and quantum annealing. The problem is also quite simple. We have a satellite with a fixed orbit around the Earth, and there are a set of image requests that come to the satellite, but it's the constraint that the satellite cannot take all of the images that are requested. So it has to select the one so that it gets the maximum value, and because every image has a associated price, associated cost. So it has to maximize the cost, complaining with the constraints. So this is an integer linear programming problem. The objective function is to maximize the cost that we get with the binary variables x sub a and j. I are the image request, and j is the camera because the satellite has also 3 cameras. So you have to select the images and the cameras appropriate so that you get the maximum value from it, but also getting these constraints that, for example, you cannot take once you take one image, you cannot take it with more than one camera. For 2 images, maybe you have additional constraints on you cannot take these 2 images with this camera, or even ternary constraints where you cannot take more than 2 images with this and this and this other camera. So the approximation is quite simple. You just transform your problem into integer linear programming and then into Cubo. And we've tried 2 architectures, one with the quantum annealing part, with quantum adiabatic theorem, and then with a circuit-based, gate-based quantum approximate optimization algorithm. And these are the solutions after it's solved, where you get in black the solutions that are feasible for each image request and each camera. We also tried some hybrid solvers because from D-Waves, only quantum solvers are limited to only 5,000 qubits and some restrictions on the connectivity of the qubits. And these achieve much more relevant results than the other ones and could handle very big problems. And from the quantum approximator optimization algorithm, it tries to optimize classically and approximate the adiabatic evolution discretely, but it's only feasible through simulation because, again, it's prohibitive on real hardware. And so these are some of the results. An efficient problem formulation is key because in this part that we've been talking about, the integer linear programming, there are many tricks you can do to reduce the size of your problem. You have also this hybrid approach that will appear everywhere in every problem practically, but still classical algorithms outperform these quantum algorithms. And for the third one I'm good on time. All right. I'm sorry for extending myself. Okay, and the third use case is about time series prediction. It's wind prediction based on the wind speed and direction for certain local areas from weather stations. And it's just a matter of solving this problem. We tried architectures like the QLSTM showed by DAS, where we have this PQC with your feature map for encoding the data and your ansatz, that it's the part that it's more trainable. And we achieved results near to the LSTM, but it's still difficult to handle because this is a hybrid architecture. These orange parts in the input and output are classical layers of neurons. We also tried more simpler architectures like the classical RNN and the gate recurrent unit with the same approach, just to compare. And the gate recurrent unit gave better results for this use case. For example, again, hybrid approaches seem to be inevitable. The Q gate recurrent unit gave better results. And there's also a very big finding that there's a great importance of designing your own ansatz for your problem. That it's a publication that we recently published, that is PPQCO, that it's Bayesian parameterized quantum circuit optimization, where you design your ansatz using a Bayesian optimization for your problem that gives much better results than using the predetermined ansatz that you can encounter. There's also quantum optimization methods. The author is around here. It's about this use case too that we've been talking about, how we solving the problem. And this paper to be published about the quantum kernels, but based on variational quantum classifiers also, satellite image classification, and scalable quantum neural networks. That it's an iterative approach. It's very interesting, and we hope it to be published very soon. So, all right, thank you. Questions? I stole this from Repsol that I saw in a presentation, but sorry.
Thank you so much. Any questions in the audience? Yep.
Yeah, thank you for the talk. Regarding the wind prediction, how far in time can the algorithm predict?
Yeah, I think we have windows. It's a nowcasting problem, so I think it's under 6 hours the prediction time, because more than that the results may get very spooky. And the periodicity of the data, I think, could be tuned to 1 minute, 10 minutes, and 30 minutes also. But the problem is, yeah, it's more nowcasting, very small window.
Okay, thank you.
Any other question?
Hi, thank you so much for your talk. In my own research, I faced the same problems regarding the encoding of the information, needing to approach it with dimensionality reduction techniques. And I was wondering if you could give some insight on which dimensionality reduction technique you used, and also which encoding you well, if you felt forced to use any encoding because of this constraint of having such a big data set.
Yeah, I think you could get very fancy on this dimensionality reduction, but we had to get straight to the point of the quantum. So we typically used PCA, and sometimes on because on the image part, one of the first steps that we did in this case of the segmentation dataset is using the bottleneck features that are the smallest in the net, so we can get like a more comprised representation of the image, and then applying to this, I don't know what was the dimension, 50, 512 or something vector in with PCA, or but nothing fancy, I think. I don't know if that was your question, or it
Yeah,
was more oriented towards.
and regarding the encoding,
Yeah.
I found that I could only use amplitude encoding, that it was the only feasible option. So I was asking regarding that as well.
Yeah, I think mostly we use arbitrary encoding, encoding each feature as the angle of a rotation gate in the circuit, so we can even encode our problem into 2-qubit or a single qubit QNN, or we don't need much more qubits, even if the number of features scales. So yeah, we encode the features as the angles of the rotation gates.
Thank you so much.
No problem. Thank you.
Thank you so much, Robert.
Thank you to you all.
The next one will be Raúl Salles de Padua from Multiverse Computing. Thank you so much.
Guys, just give us a moment. We setting things up.
Hay que cambiar la fuente en un momento. Ah, que va a poner un vídeo. Vale, pues cuando eso.
Hello, can you? Hey, good afternoon, everyone. It's a pleasure to be here. I'm Raul, Director of Engineering at Multiverse Computing. I will be presenting you today. First, our company, whoever doesn't know us, we're a startup that was being founded 2019. We're already like spread all over the world. And then I'm gonna present you guys some use cases from Kuko. And some of them, they're not direct relationship, but somewhat related. Yeah, Multiverse, we are the leading reference in quantum software. We are the biggest startup in Europe already. We recently raised Series A around 25 million euros this year, and with doubling revenue since our birth, big time. And we are right in the intersection, right, on conventional hardware and quantum hardware. So we are basically hardware agnostic. We could use any kind of hardware that's available. The main ones, big companies, also startups, in terms of like a computation. We are a team right now, like counting like more than 130 people, very diverse nationalities, thousands of citations in more than 20 scientific articles. In 2023, we had 5.5 million revenue with kind of like signaling already doubling again like this year our revenues. Just told you guys about our financing round. We have more than 15 blue chip clients, use cases, more than 50, and developing more. And we consider ourselves like as a SaaS company, right? We're a software company. We develop algorithms, make the best usage of available hardware out there. More than almost reaching 100 patents and more than 40 research publications. Yeah, we deliver value across several verticals. We don't consider ourselves like experts in any field. We pretty much focus in our tech stack, right? Which is quantum, AI, and optimization. We navigate leveraging the best from all these technologies that we have, that we use and that we develop also. Here in Kuko, we have some examples there in the screen, like Repsol. It's a pleasure being working with Ricardo so far. BBVA, right, and several others. We have pretty much all the big names in Europe from our clients' portfolio. We tend to, how we differentiate it, right? We pretty much do in our work, we are 100% customer centric. And that's what I think it differentiated us since our birth. We focus on solving our customers' problems, right? We use our tech stack to pretty much solve what we have right now, and not kind of like wonder what's going to be 5 years ahead, right? We have a research team that looks like ahead, but working with customers, and especially the area that I work for, which is customer success. We focus on problems that we have in place right now. We are now a SaaS model, including algorithms in our main ecosystem of products that we call Singularity, right? And that's what I'm gonna talk about right now. Singularity, we begun, I think, with the company's birth, more into finance, right? Into like asset management, pricing, derivatives, also risk management. But now we evolved into like have core applications into machine learning, optimization. Into machine learning, we use mainly as backend, try to leverage from tensor networks. We're one of the world's experts in tensor networks, and over there that's what we call like quantum inspired, right? Because we don't use quantum hardware essentially here. We use like a quantum inspired approaches using traditional computational methods. And mainly into optimization, and then we use quantum, right? We run the latest quantum hardware from our partners, IBM, D-Wave, and we leverage their true quantum power to solve problems that we face. I put some videos, guys. Let me just bear with me. Let me see if that's gonna work. This is the first. This first video is about Compactify, a recent launch that we just did this year. Let me hit play and see if it's gonna.
Multiverse's competing Compactify allows you to bring artificial intelligence to the next level. Current AI models are fundamentally limited by memory and computational costs. It takes too much power to run these algorithms. For example, training large language models is a gargantuan task. Companies spend millions in electricity bills to train the algorithms that do the calculations. And as insane as it may sound, this is just the beginning. These initial costs are doubling roughly every 10 months. And the customer demand for these models is also growing exponentially. Also, these models are so huge that users must run them on the cloud. There's no chance to run these algorithms on premises or without an internet connection. This is why Multiverse Computing developed Compactify. Compactify is a compressor of artificial intelligence models. It can take a trained AI model and shrink it in size while keeping the accuracy of the results. It transforms a huge AI model into something manageable and efficient, making it possible to run it on your smartwatch. Here's a demo of how Compactify works. This example uses a language model that translates English to French. As you can see, we select first the model, and then the compression rate, which can be large, medium, or low. Then we introduce the text to be translated and click Submit. The text is then submitted to two AI models, the original one with no compression and the compressed one using Multiverse's quantum-inspired technology. As you can see, even large compression rates produce remarkably good outputs, signaling that the compression did not affect the accuracy of the AI dramatically. Developers can access Compactify, and it comes in two options. One for non-experts, with a simple interface and set parameters, and an advanced one, where different parameters of the compression algorithm can be customized and tailored by the user. Compactify makes AI models faster, more efficient, and portable while maintaining accuracy. These slimmed-down AI models can be deployed on premises and other places on the edge. Compactify is quantum-inspired, powerful, and as easy as pie.
The next use case, it's on green energy transition. It's also a video. Here we do green energy transition. Sorry, for AI and optimization. We power this by our Singularity AI product in Singularity optimization.
Multiverse computing is empowering innovation in the green energy transition via the software bundle Singularity Energy. Beginning with the generation of green energy all the way to its efficient delivery to the people who need it, the bundle includes end-to-end solutions across multiple use case applications, all powered by our core engines for optimization and AI. The inventive solutions within Singularity Energy are targeted to address significant challenges in sustainability. And in addition to this, the quantum and quantum-inspired technology underlying Singularity consumes less power than conventional computational methods. This is true for all of Multiverse's Singularity products, not just in energy, but also our applications in finance, manufacturing, cybersecurity, and more. Multiverse Computing is committed to making a green impact in all that we do. Now, let's take a look at just a handful of the use case applications within Singularity Energy. First, our green energy forecasting tool makes use of proprietary quantum machine learning techniques to predict the potential output from wind and solar farms, helping to minimize inefficiencies in energy supply. Next, our grid stabilization tool optimizes the placement and dimensioning of batteries and other elements within a distribution network, ensuring stability of the grid for all the people relying on it. Other notable components of Singularity Energy are the novel quantum chemistry tools that are applied to the design of new materials for use in high-capacity batteries or simulating new reaction pathways for hydrogen catalysis. These are key components for efficient energy storage in an end-to-end green energy framework. With these applications and the many other elements contained in Singularity Energy, multiverse computing aims to be a key player in the green energy transition. For more information, visit our website or reach out at sales@multiversecomputing.
And this is like an application. I'm gonna walk you guys through for this video. There's no sound to it. Where we do the green energy production. Like it's a very simple, easy to use Streamlit app, right? That you insert the parameters, upload data, and just customize the way you want to then run the optimization, you would at the end output. Let me just pass for the sake of time. You would then output the optimal result, right? And this will be like a typical application in a front end that we develop into Singularity, right? So the next use case is portfolio optimization that I brought in to show you guys, where we use the quantum-inspired deep learning computer vision model. I'm sorry that this was a mistake. It's not computer vision model. It's like portfolio optimization. Here we.
Recording was made in June 2023. Based on version 2.1 of Singularity Portfolio Optimization for Excel. With Singularity Portfolio Optimization implemented directly in Excel, investors are able to construct optimized portfolios while adhering to an investor's preferences, such as a cap on the maximum investment allowed for each asset, individualized investment bands per asset, and a target level of risk for the portfolio. The tool uses the Multiverse Hybrid Solver, a quantum classical hybrid approach adapted specifically to the problem of portfolio optimization, allowing investors to leverage the power of quantum computing at their fingertips. In a matter of seconds, the Multiverse Hybrid provides the optimal portfolio allocations, giving maximum expected returns while adhering to the unique preferences of the investor. For more information, visit us at multiversecomputing.com.
Guys, I'm really sorry about this. This is a big typo that we had, but here we showcase what we do in a typical API into Excel. That's what finance people are more kind of inclined to use, right? And using our backend, we empower and leverage quantum into portfolio optimization. And here we show application of MPS, matrix product states, right? Where we consider still the leverage from MPS still unexplored, right? Lots of innovation still to be done there. Here we mimic the correlations from portfolios and using quantum approaches. Should then come with approximate data probabilities, therefore we can pretty much optimize the entire S&P 500, right? And that's how we can leverage synthesization techniques from quantum into finance and solve real world problems. Thank you, guys. If you have questions.
So much. Any questions in the audience?
So from the previous talks that we've had, it seems to me like other companies are in the phase of prototyping or getting ready for a future where quantum computers are capable enough that these solutions actually represent an advantage to what we have today with classical solutions. And yet, from what you've told us now, it seems like you're already exploiting current quantum computers to provide better performance than other methods. Is that true? Can you clarify? Or
Yeah, we consider it true. Of course, it depends on the problem and the maturity on a specific vertical, right? Into some specific problems we be able to leverage and implement, right? I think in a software company only like focus give us that advantage. And we always try, like I can say, like from the nature of our products and the way we conduct things, we usually benchmark against classic methods, right? And we try to overcome them, like both on performance and also other secondary metrics. Like we really think that performance, like a bold by itself, right? It's like a very convincing argument into bringing quantum development and bringing it to the market the best way possible, right?
okay, thanks.
Any other question? Thank you so much, Raul. Okay, then the next is Andres Navas from Kilimanjaro. Thank you so much.
Okay, so good afternoon. I Andres Navas Caliza, and today I'm going to talk what is Kilimanjaro and what we do in Kilimanjaro. And in the second part of the presentation, I'm going to talk mainly the projects that we have under the umbrella of the KUKO project. Okay, so first of all, Kilimanjaro was born as a spin-off of three different institutions of Catalunya: the University of Catalunya, the Barcelona Supercomputing Center, and the Institute of High Energy. And this is the founding team that you can see on the slide. We have distinguished people like José Ignacio Latorre or Paul Foro, who is an expert on flux qubits. In fact, is the actual CTO of the company. And Kilimanjaro was found by these people, but Kilimanjaro is not only these people. Kilimanjaro, we have nearly 50 quantum experts, physicists, engineers, and person who has business experience. And all these people has one goal, and the goal is bring to the industry a real quantum advantage. And with this huge group, Kilimanjaro can be a full stack company. That means that the theory teams, the applications teams, the hardware team, and the software team can work in a coordinated way. For example, the hardware team can talk with the software team to optimize several processes of control between the software, control, and hardware. Or, for example, theory and applications team can coordinate with hardware to select what algorithm will we use in our hardware, or adapt the topology of the chip for a specific algorithm. And with that, thanks to be a full stack company, Kilimanjaro can give to the user the possibility to access real quantum advantage. But for do that, we need to have the control of in each step of the process. For example, we want to give to the user a web user interface that will be easy to use.
we need to build a algorithm portfolio to solve a specific problem. We need to solve the hardware control and we need to create and to give us the device and it's okay. Kilimanjaro is all of this, but we have a great team with experts. We are a full stack company, but in real, what we do in Kilimanjaro? So we do analog quantum computing, and why do analog quantum computing, and why not digital quantum computing? Well, as Feynman said, nature is classical, is quantum. Sorry, not classical. Yeah. I have a problem. You see, nature is not classical, is quantum, and following the Feynman phrase, nature is not digital, is analog. Okay, and we have a strong ideas, argument to believe that the first paradigm that bring us the quantum advances will be the analog quantum computing. And why is that? Why the analog quantum computing will be bring in the first place the quantum advantage? The main reason, one of the main reason is the noise. Okay, typically the noise appear when the quantum system and the environment interact in a incorrect way, or for example when the quantum gates operate over the system in an incorrect way. Okay, but in analog quantum computing we don't have this. So, and we have another things that protect us from the noise. For example, the adiabatic theory, and due to all of this, we think that the analog quantum computing is the better technology to bring in a first place the quantum advantage. But we need more. Okay. Kilimanjaro has a unique technology in terms of the quantum computing because our qubits don't need error correction because, as I said, we are using analog quantum computing. But in addition, our flux qubits are good qubits because our goal is not has a lot of qubits. Our goal is has good qubits. And in addition, we need qubits that can be implemented not only Ising Hamiltonian that typically we use as a Kubo function. We need to implement more complex Hamiltonian, like general Hamiltonian with zeta x or zeta y terms. Okay, and this is it's okay, but this is not enough in a first place. Why is that? If we want really bring a real quantum advantage, we need one more ingredient in our plan, and this is the QASIC. Okay, QASIC is quantum as integrate chip. Basically, what means is we need to adapt the chip. We need to design the chip to the problem that we want to solve. If we want to solve a problem of to find the ground state of a special molecular, or we want to solve a logistic problem, we need to design this chip for this problem. Okay, and with all of that, we will bring the quantum advantage. Okay, but the second part of the talk. What we do a part of all of this in Kilimanjaro? What project? What we have on flying now in the future in Kilimanjaro? So mainly we have projects with other companies. We have projects with other institutions, public institutions. Related with the public institution, Kilimanjaro was the first company in Spain to deliver a quantum computer, a digital quantum computer in the Barcelona Supercomputing Center. And a part of this, Kilimanjaro are working with other companies like Stuart, that is a company of logistics, or we are participate in Cuco, like that is a consortium. Okay. Now I'm going to talk about the several projects that we have under the umbrella of QCO. The first project that we participate in under the umbrella of QCO project is the VQAs. We are using variational quantum algorithms. A set of quantum algorithms that are very useful in the NISQ era. And we have implemented a lot of variational quantum algorithms to solve different specific problems. Typically, this is the structure of the variational quantum algorithm. Mainly, what they do is takes Hamiltonian as a Ising Hamiltonian, and these types of algorithms search and find the ground state of this Hamiltonian, and the ground state of this Hamiltonian is represent the solution of the problem that can be a logistic problem or others. Okay. The second project that we participate is the tensor network pre-training. As I said, the variational quantum algorithms are a good algorithm for this era in where we have many qubits, and these qubits has noise, and these algorithms are ideally for this device. But this type of algorithm has a lot of issues, and for do that we use a pre-training model to improve the performance of this algorithm. Okay. One more, the Lagrange multipliers. This is for the quantum annealing algorithm. As you can see in the function that appear in the slide, we have a lambda 0 that is a hyperparameter. This lambda 0 is, as I said, an hyperparameter, and we need to select what is the optimal value of this value of this parameter, and the value impacts strongly in the performance of the algorithm. And in the state of the art, there are not too much information about how can or how the rules to select this hyperparameter. And for do that, we are working in a artificial intelligence model to find the optimal value of this lambda 0. And the last project in we are participating now is in the energy benchmark, because the quantum computers are important not only in terms of the computational power that they have. We need to understand that the QPUs will need to be a good device in terms of the energy consumption. So we need to understand how the energy consumption grow with the size of the system, with the depth of the circuits, and for do that we need to do the energy benchmark to select what device is the optimal, not only in terms of the computational power, but in terms of the energy consumption too. Okay, and this is all. Thank you very much.
Thank you so much, Andres. I have one question.
Yeah.
When you say that you modify the chips in order to tackle specific problems,
Yes.
What do you actually mean by that? Can you explain a bit more?
For example, if you have a problem that typically has a specific connection, for example, you have a logistic problem, and this logistic problem has a template, like the map of the city. It's a topology that are fixed in every problem that you want to solve in this city. And if you want to use a chip that are better for solve this problem, you will one thing that you need to do is adapt the topology of the qubits. I mean how the qubits interact between there. With the topology of the city, for example, and you need to understand what are the terms that appear in your Hamiltonian. For example, if your Hamiltonian only has zeta and zeta zeta term and x terms, you only need in your chips couplings that can be modulate this coupling. I'm not an expert in the hardware, so
Thank you.
Take care.
Any other question from the audience? No. Thank you so much.
Thank you very much.
The next one is Repsol, Ricardo Enriquez. Thank you so much for coming.
Well, first of all, good afternoon, and thank you for this kind invitation to this important forum. And okay, I would like to talk today about what has Repsol to do with quantum technologies. That's probably the first. And I will repeat many other messages that other KUKO members said, and I'm happy for that to happen because that means that in KUKO there's some kind of collaboration and some kind of common message. So let's talk about first Repsol. So Repsol probably is well known for the gas stations, but in fact it's a multi-energetic company and it's spread over the world. And it's multi-energetic since it moved to also renewables, electrical mobility, and so on. And this is the big part, but I come, and it's less known, I come from the Repsol Technology Lab. It's a research center that we have close to 300 experts, scientists, all over, covering all over the energy transition technologies. And we have also a corporate venture. We have a fund that it is now, I think this is something like obsolete, but we have some millions to invest in startups and to promote technology. And okay, this is very good for the actionists and so on. But what I like when I present Repsol is this slide. Repsol was the first company all over the world to announce the net zero energy commitment emissions by 2050. And we have a plan. And we have a plan, a very detailed plan. And we have a technological journey to decarbonization. So we have a clear idea of what we have to do. A clear idea, or not so clear, because we know more or less the technologies that we need to use until 2030, but we have less idea, more uncertainty of what technologies we need to do. What would we for sure know is where are we going? To the left, you have, let's say, business as usual. You have a refinery, oil coming inside. You have a feed by electricity and natural gas, and your output is some chemistry and fuels. Okay, this seems very simple, but in fact, it's a very complex situation. Think about that you are feeding at least half of the fuels of all the country. Now let's move to the situation where we want to go. And our feed will be organic residues, plastic waste, oil for sure, biogas. We will feed by renewables. Renewables are intermittent sources. And the output will be a very broad kind of fuels. Synthetic fuels. We need to capture CO2 from atmosphere eventually and put it inside other products, like what we call synthetic fuels. So in this context, I told you about the second quantum revolution, but I think in this forum, it's quite clear that the first quantum revolution happened something like 1 century ago. And the first quantum revolution is, I like to put PV, and PV changed the world. And if you want to be in the energetic sector, you cannot get rid of PV. And in fact, Repsol has a lot of PV. So the second quantum revolution probably will be very important. So what we do? Okay, let's make a team. I'm the head of the team now. We are 4 or 5 people, and let's catch all the knowledge and all the different parts of the company. So let's go as one. There's no digital, corporate mentoring, and multidisciplinary team is very important. And also, we need to deal with different technologies. I will talk today mainly on quantum computing, but also related to cybersecurity. It's very important, the Q-Day, and Repsol needs to be prepared for security. And also there's quantum sensing. For instance, very precise gravimetry, and gravimetry is very important for us. So what to do once you have a team? Well, we vinculate this new computing, because the computing will not be for today, it will be for tomorrow. Tomorrow there will no be something like a quantum laptop. We need to wait some years, decades. Hopefully Kilimanjaro will do something, hopefully. But we need to look for hybrid solutions. And we know that there's something like a supercomputing, and we will have quantum computer, and somehow they will be mixed, they will be hybrid. At this point, we need to say that at Repsol, we are not academics. So we are not interested in principle in learning the traveling salesman problem. We need to go to the real cases and to look internally what we want to do. And we are also agnostic. I mean, I am a quantum optimist, I say. But what I want for Repsol is a good solution for my problems. But the real thing is that we need to be prepared. And the sailing of this approach is that we need to understand. We need to understand how quantum technologies work. What I like to say when I talk is that Repsol is not making engines, but Repsol needs to understand very well engines if you want to produce something. So we are not developing hardware anymore. We are the users, and I will show you some of the use cases right now. But we need to understand how to translate our problems to the quantum realm. We look inside, but we also look outside. And outside, we need to co-develop. You can have a lot of talent in Repsol, but there will be always more outside Repsol because the world is bigger. So we need to share with others. We want also to catch investing in startups, for instance, Kilimanjaro, Repsol have a special relationship, but also establish alliance with academia, with big players in quantum computing, and making consortiums. We must say that, for instance, Repsol and the Barcelona Supercomputing Center have a very close relationship. In fact, the building in the Mare Nostrum 5 is made by Repsol. So we have a very, we need always to be close to the academia. And to minimize the risk, we need to go with audits. And this means participating in R&D programs. And the CUCO project is one of the main examples of participating in our public funded R&D programs. So we apply, and we had the chance to participate in this CUCO project with a clear idea, with how can we apply quantum computing for a sustainable energy sector. And you cannot do it alone. You have seen many times CUCO, and how Repsol puts the quantum strategy over CUCO. And you see 3 lines. I will talk you for each one now. First, we have a problem related to optimization. Optimization is quite ubiquitous in the industry sector, logistics, or whatever. I put then quantum computing for chemistry. Okay, strictly sensing, it should be simulation. But simulation in our field is mostly chemistry. And at the end, I will talk about quantum computing for machine learning, and I will say some personal opinion, just to be provocative. Okay. Well, one of the first use cases we look for is what we call virtual power plants. So there is a phenomenon that is called renewable energy curtailment. I mean, the biggest and the greatest engineering opus of mankind is not the internet, it's the grid. So the grid needs to match supply and demand on real time. And okay, if you want to do that by buying a storage just to catch all the renewable energy, because renewable energy is intermittent, that makes no sense. It's quite expensive. But if you have an advanced control system for each home, you can, let's say, control 1 kilowatt per home in a 24-hour forecast. 1 kilowatt per home, if I can add, let's say, 100,000 homes, I have 100 megawatts. 100 megawatts is a power plant. So I can get all the homes together to act coordinately to participate in the energy markets. So the consumers, one single consumer with 1 kilowatt, they cannot participate. So this is a problem, and I need to build an offer for the system, for the energy system, each 15 minutes that it covers 24 hours. And I need to catch from different bricks coming from different homes. That is what we call a combinatorial optimization problem. A combinatorial optimization problem is very suitable to be applied for analog quantum computing, as we said. You can map it to a is in Hamiltonian. Okay, I think I did not put the details here. No, much better. So we did this, and we did it in collaboration with multiple people, and also with the Barcelona Supercomputing Center, and we saw that there is some. We ran it in the wave, and you can see down. This is the executions. This is the size of the problem, the number of houses I have, and this is the runtime I have. And we can see a clear advantage in computing time with respect with classical simulators. But all that glitters is not gold. Many times the solutions you get have not the quality you want. You have a lot of constraints, and you need to fulfill all the constraints. On the other hand, there's the question of Lagrange multipliers. Not always is easy to formulate that Kubo problem that is in Hamiltonian. And in fact, when you move to a different situation, there is another problem. This is the Hamiltonian gap. And you never know, you cannot know in principle if this Hamiltonian has a gap and can be simulated efficiently in an analog quantum computer. So we see that we can learn something about this, but probably we need to hybridate somehow to get better sizes. And I think it's promising. It's promising, this field. This is a combinatorial. Let me show you a couple of use cases more. And there is a ubiquitous problem in the energy sector, is the optimal control one. And you can formulate the problems to the optimal control one from different places. I think you can control the quality of hydrogen in a refinery, or you can think how to produce efficiently green hydrogen, or even logistics planning. We are running and we are making 100% renewable fuels. And that means that we need to buy mainly all the waste of Spain. So that's a big problem. I mean, and we can formulate this way. And this way, we can formulate like what is called model predictive control in an open loop scheme. And for most of you will be familiar this formulation, that this is some kind of functional I need to minimize with a constraint for a differential equation. Well, we have two different approaches. One approach is discretize the system, and then now I'm in the middle. Discretize the system and then optimize, and we are exploring quantum walks. And we need to say that if you discretize the system, you need to put a lot of constraints, and we need to do it automatically. You cannot do it by hand. So with the help of Kilimanjaro, we are making an automatic transpiling of these problems. Otherwise, quantum computing will not be useful. The other strategy, thank you, Mr. Chairman, is to quantize the system. I think is to map this. If you see that, you can remember something like the Hamilton-Jacobi equation that you can map to the Schrodinger's one. Okay, let me go to the next situation, is simulation. Chemistry. Chemistry is a hard problem. Okay, I will be very fast what we are doing. It's very simple when the problem is simple. When I take the hydrogen atom, I can do it by hand in principle. We all did it when we were childs. But when the system is growing, it's growing in complexity. So that's why we use approximation methods, and mainly there's one theory. It's called density functional theory. That is mainly used as the workhorse of chemistry simulation, but it is not always precise. So probably makes sense that in some systems that are really quantum by nature, that I can put these models. Okay, how to move to that? There is a workhorse, also the variational quantum agent solver. Okay, but with the size of the systems, it is not enough, even not enough, because even if we restrict to an active space, the devices, the quantum devices, are not big enough for that. So in our help come the embedded Hamiltonians. I will not get into the details, but you can take a part and simulate it in a quantum device by the influence of a mean field coming from the rest of the system. That's the idea, and that's what we did it. And where we did it for hydrogen production. We will need a lot of hydrogen, and the hydrogen we want to be cheap. And why it's not cheap? Because catalyzers have platinum, have precious metals. So we need to understand very well how is this system if we want to substitute those metals and get cheaper hydrogen. We are producing hydrogen at this moment, and what we did was to simulate exactly a part of the system as a benchmark, and to produce the BQE. You can see this is the executions on an IonQ, and we also got a new algorithm that is quantum selected configuration interaction. I will not get into the details. That you can see here. It does not need learning anymore. We are doing this for hydrogen. I'm coming, Mr. But we are also doing it for CO2, for CO2 to produce synthetic fuels. Okay, I did not put the details, but we want to replicate and to see. Probably in the colloquia we can speak more about this if you have any questions. And finally, as I promised you, just quantum computing and artificial intelligence, and I took this picture. This picture will be somehow the energy system in the future, in 2050. And you see, first of all, is complexity, so you will need IA. And why we put the quantum IA at the end? Well, two reasons. When we started UCO at Repsol, Repsol has a strong IA strategy and a digitalization strategy. So the first of all is do not disturb those guys. Let's learn quantum, and let's see in the future right now how to do that. The second rationale is that it has been mentioned before, that typically they require a lot of data, and the size of the devices actually is not very big. So if we want to catch a lot of data with quantum computers, we need to wait for some time. But there is a third rationale that is more mathematical one, and this is coming from my personal opinion, is that what is called the general approximation theorems. So IA is mainly based in deep neural networks that have billions of parameters. And there are theorems that if I give you any function you like, you can approximately efficiently with a deep neural network. So what has quantum to do with this? And the answer, I think, is that we still don't know qualitatively what quantum can add to the deep neural networks. I think we don't know. So we need to understand better. But in the meantime, probably, and has also been said, and also we are doing at CUCO, probably the large language models that also Multiverse mentioned can be trained more efficiently, and we can look for green hydrogen. I'm really sorry, Mr. Chairman, but I think it was more or less important to tell you about that we are doing at Repsol. So, any questions?
Thank you so much, Ricardo. Any questions in the audience?
Come on, guys. Que está muy chulo.
How big is the team that you have, or it's you are collaborating with different departments, right?
Up to 5.
Up to,
Up to 5.
you
But
are
they are artists. They are not programmers.
okay.
No, but we establish a lot of collaborations. Our developments in house are more related to soft code. That's why we have an open framework. It must ask others, and Kuko is one example, but we have others.
Okay, so thank you so much.
Well,
And the last one is Zenaida Hernandez from BBA. Thank you so much.
Hello, everyone. Can you listen? Okay, so it's good that I made like a very short presentation because because we are yeah. So first, I would like to tell you a bit about BBVA. We are a global financial group with 74 million active customers and 121,000 employees, more than that, as of March 2024. We operate in more than 25 countries. We have a leading position in the Spanish market and also are the largest financial institution in Mexico. We also have leading franchises in South America and Turkey. And we also have an important investment transactional capital markets banking business in the USA. We contribute with the activities of our stakeholders, which are shareholders, clients, employees, providers, and society in general. And we do that with a unique value proposition leveraged on technology, innovation, and data. And within this innovation, we also, well, I am part of a quantum team. And this quantum team has been working since 2019 with the purpose of finding applications of quantum technologies to the financial sectors and in general helping prepare the bank for the changes that may come, the advantages and the threats. And here we have a very small overview of the projects where we have participated or are participating. Then you have Kuko here. We have also participated in Caramel project led by Ispasat. We are collaborating with Lantic, an organization of Basque Country. And we are also part of the Quantum Safe Financial Forum, which is led by Europol, which is an agency for law enforcement collaboration at European level. And as areas of interest, we have mainly 4: optimization, simulation, machine learning, and cybersecurity. As for collaborators, we are currently collaborating with CSIC and Tecnalia, which are Spanish research institutions. This is within the framework of Kuko. And we have worked with different companies in the past. We have worked with Multiverse, which is here. We have worked with Zapata, and we have worked with many others. I'm just adding here some of them. And we have been lucky to be able to publish some of our work, in particular in optimization. Last year, we published a work that was the result of the collaboration with CSIC. And that was a new algorithm developed within the framework of Kuko and its application to a finance problem called cash handling. For simulation, we worked in the past with Zapata in quantum algorithms for a problem called credit valuation adjustment, which it's a problem where you want to take into account or to estimate what's the price taking into account some risks. I'm not going to go into details now, but if anyone is curious, I welcome to questions. And the third, that will be machine learning. We recently have a preprint last year, and this consisted of the application of a quantum-inspired method called tensor neural networks to price and with assumptions, and this was a result of a collaboration. And said that, like, I wanted to say something else, like, for example, a little bit of the context of the problems, but given that there's a little time, seriously, afterwards in the coffee break, anyone can contact me and I can reply details or give more details. And now, how we have participated in KUKO? We participate in 4 research lines. In particular, 2 of them are focused on optimization. The first one also in simulation of sustainability problems in the financial sector and logistics. These first 2 lines, we collaborated with CSIC. The third one, we focus on machine learning. This line, we participate in collaboration with Tecnalia. And the last one, we participate in problems related to simulations, optimization, sustainability, and risk assessment. This has been in collaboration with CSIC and Tecnalia. And the first 3 lines are concluded because KUKO is finishing this year, and little by little we are finding its fruits. So I want to highlight now some results that correspond to these lines very briefly. So for the first 2 lines, we want to highlight the development of a new algorithm, a gate-based quantum computing algorithm called MOVCO-VQA. This resulted in a publication that you can find reference here. If anyone is curious, you can take a photo and check it later. And this corresponds to it's a graphic that explains a little bit how the algorithm works. It has some quantum computer part, some classical computer part. It's a kind of a combination of 2 methods, one quantum variational algorithms and another one genetic algorithms, which are a type of classical algorithm. And we were able, with this algorithm, to successfully solve cache handling problems of small size. This problem was very interesting because it's very difficult to formulate efficiently as a QUBO due to a large level of constraints. And to our knowledge, this was the first attempt to solve this problem with quantum algorithms. So this was actually, we consider that added value for this particular problem. And the second highlight is the development of generative algorithms with tensor networks, which are capable of recreating probability distributions and through that solving optimization problems. Within these optimization lines, this was the only algorithm that we developed that didn't require sampling during the training process. As for the last line, we want to highlight here that we obtained some results with quantum supervector machines that here the other members of KUKO, some of them already work on this. In this case, we didn't find qualitative advances compared to quantum-inspired methods, but this helped us to identify aspects to be improved for the development of new quantum algorithms, in particular that we had to improve training time, and also the selection of better ansatz. And we are currently working on a new quantum algorithm based on the different learnings. And in fact, this is an image of the results of the new quantum algorithm, but this is in the last line, and in the future, maybe we will be able to share more. And the last highlight here is that we were able to implement a quantum-inspired algorithm. These 2 algorithms were implemented for the same problem, which is the anomaly detection problem. Again, if you need more details, I'm available in the coffee break for any question. And what we found interesting here is that the performance of the algorithm was competitive with respect to classical algorithms, such as gradient boosting classifier, which is very known for classification problems, and supervector machines, the classical version. And with this, I want to thank you all and welcome any question.
Thank you so much. Any question in the audience? I think everybody's tired.
At the beginning, you mentioned that you have a relatively large team, the quantum division.
I didn't mention name, but number. We are currently 3 at the moment, but we will be 5 at the end of the month. We are kind of changing now. But in the past years, we have been 5.
Okay, because I was going to ask these proposals, these different lines that you explained. They were in collaboration with CSIC, some of them, and other institutions.
Yeah,
How much do you do in-house, and how much is carried out by the partner in its case?
I would say that it depends on the research line. So with Tecnalia, for example, we have done some part, and they have done some other part. And with CSIC, maybe we have provide more the business side of things, and also with the paper, we help during the redaction, and everyone was happy. Yeah.
Okay, thanks.
More questions? No? Then thank you so much, Zenaida. We will do a short break of 25 minutes or so, and we'll come back with the roundtable.
Hola. Hola.
parecía muy interesante.
Isso, para...
Solo lo usáis para eso. Y la porque las sensores de calidad como se aplican normalmente cuando venimos eso me cuenta esa en este modelo.
A parte de compactifiers, tensioneters implementados dentro das con LLMs, lo que tenemos es un decoders. Entonces, tenemos metros, principios son los... Pero tenemos, también tenemos para visión.
Pero claro, o sea, porque claro, pues, dependiendo de la función, hay algunas funciones que son estables, GPS, pero digo, claro, por ese tipo de problemas.
Sí. Bueno, por ejemplo, ahorita estoy poniendo una patente de pie con data privacy, usando NPS.
También.
Se comprobó mejor que cualquier GAN.
Ya, pero es heurístico. Es heurístico. Ya, con lo mío también, a veces.
Ajá. Lo que se pasa al final es que con inteligencia artificial, cuánto puedes pegar con esto todo lado. También tenemos arquitecturas que son solo Deep Neural Network. Si caso de uso no se comprueba que hay, se el mejor caso no utilizamos tampoco tensorización. Hacemos los estudios, intentamos evaluar las ventajas de final, lo que direcciona es el caso de uso, ¿no?
Que probar todas las herramientas que tengo. Más que a desarrollar como una esa herramienta interesante mucho. Muchas veces el tema de investigación es más como al revés. Que busca, que desarrollar una y ver más posibles aplicaciones o eso. Que no tienen tanto.
Este faz porque todo mundo hoy aspira y con GNI es una vertical nueva. Aprendemos esa parte cuántica se aplica como vertical en parte generativa. Probando también, ahora pasa que grande hype es con T-Mobile, T-Model 4 Omni, dentro que hicieron ahora. Estamos con los LLMs, también nuestro equipo de research este año haciendo investigación con parte de transformación. Hicimos bien visualización de CNNs con segmentación de imágenes. Estoy trabajando también con detección de objetos, añadiendo al toolbox que tenemos de edición. Nós estamos assim tentando com nosso benchmark, que eu creio que será YOLO. Porque, por exemplo, com GNI, CR, todo esto, tampoco aún están bien. Porque para poner mismo GPT-4o es buena, bueno, pero al final, en caso de uso, hay requisitos más rigurosos. de performance, com a latência, do que o curso especializado. Né? Então, tendremos um tempo para todo o resto prevalecer.
Pincha aquí. Esa era mi pregunta.
No, pero si la quieres, se la ponemos.
Ah, bueno, no está mal, aunque igual vale.
¿Quieres silla? Agua, sí, la cojo en la fuente de la entrada.
Sí. Oye, yo no te preocupes.
No, ya.
Ah, es que se cubre exactamente lo mismo. Es que hay un panelista que no sé. Ahora. Ah, perfecto, no. Ya, y con esta se ve la otra mitad. Y no, ¿qué partida? Voy a intentar. El ordenador.
Ponemos cámara.
Sí, me parece, sí. Bien, Jesús, muy bien. Vas a hacer una atentita.
Pero igual podemos cambiarla. Yo no lo sé.
A ver, para la verdad que pase esto en pequeño.
Bueno. Igual sí está bien, ¿no? Preferiríais invertirlo y que fuera tan pequeño igual sí.
Lo mismo.
¿Qué es eso?
Habrá que ver qué tal queda la cabeza de Robert.
Porque está como preparada para salir corriendo. Eso. Lleva la mochila brochada y todo.
Le gusta pegarme.
Vamos a ver. ¿Qué tal, Raúl? ¿Te gustó la presentación?
Linda.
Un poquito de esto, un poquito de aquello.
Bueno.
No, pero que a mí me gusta porque se ha complementado muy bien los roles también.
Sí, vale, sí.
Era un poco, el poco queda bueno.
Química o interesante.
Tenemos que hacer alguna performance para presentar una CDT. No, algo así. Pero. No, pero digamos que eso.
El tío del CDT mirando la reunión.
No, al CDT tenemos que presentarle los resultados de grupo.
Espectacular.
No, tiene que ser algo que
Mucha purpurina.
En Bernabéu, en Wanda, con gente ahí, ¿sabes?
Sacarlo ya.
¿Los demás también queréis hablar?
O lo que queráis.
Solo para ti.
Los demás.
Estaba pensando.
Los demás queréis hablar.
Creo que es mejor, ¿eh?
Sí.
Sí, no lo has oído tú. ¿Has trabajado?
Sí, hombre, un poquito. ¿Hay alguna pregunta?
Yo también, pero porque tengo que coordinar con ESCO, porque es la primera vez que hago esto.
Ah, para que esto no diga espectacular y tú digas.
Porque en realidad no, pero podría pasar, entonces va a intentar coordinar bien.
Bueno, yo contestaré solo a las que me parezcan bien. No lo sé. Te pido para contestar. No lo sé, yo digo. ¿Raúl?
En esta cosa hay que tener cuidado.
hay que tener mucho cuidado siempre.
Right, so we can start now. So good afternoon, everyone. My name is Alejandro, and I will be the person moderating this next part, which is the panel session. And first, I want to thank the organizers for putting together such an amazing congress, as well as the companies involved in the Google project that have made these sessions possible. For anyone that couldn't attend the focus session, let me just give a very quick recap of our panelists here today. So starting from the left, we have Robert Fazan Rodriguez, who is a data scientist at CMV. And then we have Raúl Sáenz de Padua, who is Director of Engineering, AI and Quantum Computing at Multiverse Computing. We have Zenaida Hernández Santana, who is the Area Transformation and Performance Manager of Quantum and Innovation at BBVA. Then we have Alberto Martínez Fernández, who is a Junior Researcher at Dash Photonics. And we have Ricardo Enríquez Miranda, who is the Head of the Quantum Technologies team at Repsol. And finally, we have Andrés Navas Cáliz, who is a quantum engineer at Kilimanjaro Quantum Tech. So the topic for the roundtable is the future of quantum technology and real-world applications. So we will dive deep into the long-term vision, combining both technical and business perspectives. We'll give a roadmap of quantum technology development and its anticipated impact on various sectors, and we'll wrap it up with the profiles that will be needed in this race. But before talking about the future, I want to kick things off with the present of quantum technologies, and I want to start with you, Zenaida. So I want to ask, how do you see Spain and Spanish companies in the global quantum computing race?
Okay, so we see ourselves really well at the European level, but we are like a little bit behind compared to major players like USA or China. And also another thing is that I think that thanks to QUCO and Spanish projects similar to QUCO with public funding, we have been able to position ourselves better within the European sector. And I would like to invite my co-panelist to reply as well.
Yes, please.
Hola. Nice question. Thank you. I think there are at least two levels. One is the European level, and the other is the worldwide level, probably. At the worldwide level, I think we must correlate within Europe. I mean, Europe is racing for the quantum, but we must recognize that Europe needs to improve and need to do something more. So, European companies are in the framework of Europe, but inside Europe, Spain is very well positioned. It's very well positioned from the number of startups and the number of companies that are doing things and doing the first steps in quantum. And one example is one initiative coming from the European flagship is the QUIC, is the Quantum Industry Consortium. And in the Quantum Industry Consortium, you see that there are as many companies from Spain as from Germany. And that's not very common from the European side. So from the European dimension, we are very well positioned. From the world position, hard to say. What I can add is that probably, at least on QUCO, we have nothing to envy others. And we are doing, and this is a big bet, and we are doing things. We are at the level. But we must realize that quantum computing is a long race. It's not a sprint. So it will be something like a marathon. So that's probably my opinion. I don't know if some of the colleagues want to add something.
Yeah, can I get your thoughts, Raúl?
Can you? The way I see, like, I don't come from Europe. I'm from South America, right? The stage of development there is still even before here. In a global scope, the way I'm seeing, like, especially talking about multiverse, we were comparing ourselves like last year more to Sandbox, like it's a spin-off from Google, right? But Sandbox also does like hardware, right? They develop their own hardware. We're only a software company. Nowadays, we're comparing more, to be honest, with PyTorch. So I think we're still in early stages to define like who's gonna be the winner. If it's that gonna be at all like an all-time winner, like that's gonna dominate the whole thing. At the end, I think it would come to the applications, right, and solving real problems. If quantum comes to be advantageous, if it's like a hybrid, quantum inspired, whatever you call it, approach, what should prevail will be solving real world problems, right? In delivering value to society, to customers, to that's what's gonna at the end. That's my humble opinion.
I want to continue with you, Alberto. So I wanted to get some insights from a business point of view, but also from a technical point of view, as to why quantum technologies are such a hot topic right now. So my question is, what is unique to your quantum technology as a selling argument between other technologies?
In our company, where we work on defense and space, quantum computing offers clear advantages against classical technologies, as photonic technology shows advantage to electronic technology, and that's why in DAS Photonics we use photonic circuits and instruments. For example, in defense, some of the, I will say that the three main quantum technologies that could add advantage in the next 10 years will be quantum computation, quantum communications and encryption, and some technologies like quantum magnetometers. And those technologies show clear advantage in the defense area, in the defense sector. And I would say that there's we can't really even compare, for example, quantum communications to classical communications. Once we achieve an application where quantum encryption and communications works properly, classical communication cannot compete with it because it's almost impossible to break. And for example, with quantum magnetometers, which is an application which helps UAVs to be well, not flown because they are autonomous, but they help them fly without GPS. And nowadays, for example, in Ukraine, we have been seeing problems with jamming where drones cannot fly properly due to those problems with GPS. And quantum magnetometers and quantum instruments used for UAVs give the UAVs a precision flying that cannot be achieved with classical instruments. That's why, for example, those classical instruments were abandoned for GPS because GPS was more precise. And with quantum technology, we achieve an accuracy with the flight that is similar to the classical one with quantum advantages. And those quantum advantages are the ones that make those technologies better than classical counterparts.
What are your thoughts, Andres, on the matter?
What can I say about that is you can think and you can see the quantum computing or quantum technology as a tool, like a hammer. And probably hammer is not the best tool for all the tasks that you need to do, but it's a new tool, right? So what we need to understand now is what we can do with this tool and for what, okay? And this is the challenge today. It's obvious that the quantum computing or other technologies like machine learning with quantum computing or other things will be useful for different tasks or different goals, but we need to understand why and for what. Yes.
Finally, can I get your thoughts, Robert?
Yeah, I agree a lot with Andres because partly I don't think that. Let's take this from also my personal point of view. I don't think that we're selling anything right now as a product, or that we should sell nothing because we are at a preliminary stage of finding out what we how we want to use quantum computing for, what is this tool, in what use cases it would take advantage from classical computing. So yeah, I think it's a very useful tool, but we're still trying to figure out where and how to use it. And it's not just a matter of selling humo, as we say here in Spain. So yeah, I think Andres' take was very nice.
Right. Thank you. So now wrapping up this more business-oriented part of the panel, I really wanted to ask you, Ricardo, what does a company look for when discussing new business plans directed into emerging technologies, such as quantum technologies? Like, what factors are taken into account in the decision-making?
I think quantum technologies at that dimension are not very different from other deep tech technologies. I mean, we are at Repsol, we are facing always low TRLs. The difference probably is the potential impact, the revolution by itself. But from the business point of view, I mean, the methodology is the same. We have a department on deep tech, and we are always looking for new technologies. And quantum technologies are the new kid on the block at this moment. But from a methodological point of view, I think there's no much difference. The difference will be on how long will you keep the expectation, because it's very difficult at this moment. It has a singularity somehow. It's very difficult to see the potential impact, because we don't know. We have quantum advantage for sure for sensing and for cryptography. That's a fact. So there's nothing new there. And related to computing, well, we have no quantum computing advantage at all at this moment. And if we have the quantum supremacy, what is the impact? That's the key point. I mean, the rest of the methodology, same. It's a deep tech.
Do you think that we will maybe see a change when we get to that impact or those first real advancements?
Well, to be honest, it's a very hard task. It's a very hard task to assess that impact, because it will depend. If you say, okay, I will have an impact that is infinite, then I can wait infinite. But some guy needs to say, okay, the impact will be this. And it's hard to say, because we have two things, in my opinion. Let the colleagues for sure to add whatever they like. But we have the acceleration, and we have the enabling. The acceleration will not be the high potential. The enabling is the high potential. But you don't know today what is going to enable. So hard to say. I don't know if my colleagues want to add something.
So I want to say something to complement. Like, for example, in order to build a strategy, we trust on reports by renowned groups such as McKinsey and Boston Consulting Group, because it's very difficult to estimate the potential impact. And they have groups of people that have been doing this for different technologies for many, many years. So we typically trust the numbers as what we can expect. I mean, knowing that it may change, but as a first figure of merit, it's very difficult to estimate. So we trust initially those and try to keep updated. And together with that, we try to look what other businesses are doing globally, because that usually gives you the more updated information in terms of like, in our case, not the financial sector, the more financial sector, what financial sector has other quantum groups, what they are publishing, things like this, and what they are working on, if the information is available, because it's not always available. And last, we also try to listen to experts. So if we are in particular forums where there are experts that are trusted, for example, for quantum safe security, it's the case, then we try to listen what they are saying, or looking for reports that are based on what experts on the particular technology are saying. Like, for example, the question that is very difficult is, when do you expect the quantum threat will be happening? No, like this is super difficult. So in order to solve this, they ask a lot of experts, and they did statistics on the range of years that they thought it's going to be, probably not now, probably maybe on to security to be now, and like different ranges. And that was the closest to expert opinion that, well, at least I think that we can have at this moment. It's kind of difficult. And the technology is so disruptive. There are so many different types of quantum computing, and with different roadmaps, that you may say something now, but then there's a new quantum computer based on a new different technology, and it may change suddenly. So it's very difficult. And that's about me. Yeah.
Yeah, I mean, following up this conversation, I wanted to ask Raul, in your opinion, how close do you believe the mass market is to adopting these new quantum technologies, especially quantum computing? What sectors do you think will be the early adopters?
I think, no, we're already seeing that, right? Some whatever sector that we have shortcomings in the classic computation, quantum is already prevailing, right? If you take optimization, right, when you have quadratic cost functions, such as finance sector and so on, we see like already like quantum prevailing there and really thriving there. I don't really believe there will be like a prevailing sector driving the whole quantum leap. And sometimes it's also hard to distinguish, right? Some companies are doing quantum but not disclosing, right? If you see between the lines, like in some launches that you see, especially in big tech, right? Yeah, we just saw now like Apple launching like AI like shrank into mobile devices, right? Also in partnership with OpenAI. There's also a quantum algorithm under the hood there that no one's disclosing, right? And I was studying like within Multiverse, there's like an open source like tensor network library by Google, right? That you can just go there. There's like this whole tutorial, lots of courses, videos, and so on. So they're doing like this, like it's not now, right? At the end, I think the quantum leap will happen at small increments, and once we realize quantum will be here already, like everywhere, spread the same way we're seeing like AI is the world breeding AI, right?
Can I get your thoughts, Alberto, on the matter?
I think we have to distinguish between quantum technology and quantum computing. With quantum technology, there's already advantages, as Ricardo said, in sensing and communication, and in Dash Photonic, we are implementing them or researching them because we know they are going to be the future. And in quantum computing, it's hard to say, because first, we need a breakthrough in the hardware. Right now, the hardware is a huge limitation, and there are several algorithms that show advantage but cannot be implemented. And second, there's a problem with the quantum-inspired classical algorithms. We have seen lots of quantum algorithms that they beat classical algorithms, but a couple of months later appeared a quantum-inspired classical algorithm that was better, more efficient, etc. So, in my opinion, I think it will be a combination of breakthrough in the hardware and then something that forces us to change to quantum computer. For example, the energy consumption. Because we have efficient classical algorithms and classical computers that can do the job. Maybe they are a bit slower, maybe they are not that efficient with data, but they work. And for a company, the fact that you are going to be a bit faster, maybe they are not going to want to invest because that's a lot of investment. But with energy efficiency, since it's going to be a clear requirement in the future with green transition and the energy consumption that we are going to see with artificial intelligence that is already increasing, I believe that once we have that breakthrough and we see that there's quantum computers capable of implementing the algorithms that we know they have advantage and they show clear efficiency in energy consumption, we will see a fast, well, maybe not a fast, but a clear transition with lots of companies investing at the same time in quantum technology, like, for example, we see now with AI.
Can you weigh in on that point, Andres?
Talk about the breakthroughs that are necessary in the hardware?
Yeah, no, mainly about his point about energy consumption. What sectors do you think will be the early adopters, if any?
The sector that can pay the technology in the first place. This is obvious. Following that, I think that the bank, in the defense industry and sector that have a lot of budget. This is, in principle, the first sector that will be adopt the technology. But following the argument that the College of DAS said about the breakthroughs, it is true, completely true, that we need breakthrough in the hardware part. Like, we need qubits with more coherence time, we need to understand how to reduce the noise, we need to understand how can scale the production, the size of the chips, because in the classical industry we can make chips with 1 million, 1 billion, 1 trillion of transistor, yeah. But we don't know how to do this with quantum chips. We have a lot of things, a lot of challenge that we need to solve in a first place if we want to start to think about okay, I have a full tolerance QPU, what can I do with QPU? But this is hard to solve, but at the same time we have a problem in terms of the quantum algorithm, because it's not trivial to think about a problem that in the quantum computing will be better than the classical algorithm. And I think that this problem is more difficult than the hardware, because in hardware you have it's clear the problem that you have. Okay, you want to reduce the noise. Okay, this is a specific problem, and you can think, but in theory, the land of ideas is much greater. So it's hard to find a good solve.
Yeah, Ricardo.
Yeah, I want to say something that I think it will not be by sectors. It will be by applications, because you have computing everywhere. Every sector has computing, so it will be the application. And as I told in my talk, there are applications related to optimization, but in optimization, once we have some small advantage, that will be for reliable computing, that will be adopted for sure. And okay, but that will be a small advantage, but because we are optimizing since the Second World War. And it's a very competing place. We have a lot of software, and we need to compete with GPUs and so on. So, okay, we cannot expect a big thing. So that will be a question of money. And the other application I told it was simulation, and we need there for real quantum systems such as new materials, topological materials, places where, for instance, the Bohr-Oppenheimer approximation doesn't work. I mean, and that's the important issue. That we do not have an idea. As far as the roadmap is being said, the main line of thought is that I will have a fault-tolerant quantum computer by 2030, and in the meantime, I will use the NISQ. But they are using the NISQ as an accelerator. I mean, you are formulating the problem as a DFT problem, so you cannot expect going beyond. So we need to figure out what we don't know. So that's why, and it's related to how we manage the expectation. What can you expect? But for sure, in the applications of optimization and simulation will be for sure adopted. And all the sectors, I mean, chemistry, pharma, energy, we are all doing simulations. We're all doing optimizations, and it's not a matter of sectors. I also said that I have no clear idea of how will be related to IEA, but just to point out, I think it's important. It's not by sectors anymore, I think.
Finally, Robert, can I get your thoughts on this? Like, what applications in your own personal experience from GMV do you think will be the most important?
My answer might seem a little depressing, but as Andres said, and also Ricardo, it's hard to tell by application or by sector which problems will be more suitable for be solved by quantum computers or algorithms. So yeah, it's a matter of trial and error most of the times. As Andres said, you don't have a very defined problem as you could have in hardware. It's just a matter of trying different options. It might seem that optimization through quantum annealing can be a little more promising than, let's say, quantum machine learning, as there's more skepticism, as Ricardo pointed out in his presentation. That could be a little guidance. But yeah, it's hard to tell. I think we don't have a defined answer.
Hard to say that when you have a baby, what will be in 10 years? What will be studying? That's more or less the question you're asking, Guy.
Yeah, I see. I wanted to continue, and Andres touched a bit on this as well. A bit more technically, like, what do you think the primary challenges are when implementing quantum solutions in real-world industry settings, or at least the conclusions that you got from these highlights that you presented today for the Google project? We can start with you, Alberto.
Talking with the Dash Photonics vision and where the areas where we work, the biggest problem is hardware. For example, quantum key distribution for the communication between the satellite and the ground control that we are developing. The theory is clear, we know it, it works, quantum key distribution, the encryption, etc. But designing and building the instrument, the application that will create the single photon, sending it to a satellite that is moving with an atmosphere between the ground control and the satellite, you have to be very precise, and you have all the noise of the instrument, all the problems generating the single photon, the fact that maybe you are not generating a single photon because the technology needed for that is more complicated than the requirements that you have in the project, etc. There you have a clear problem, and that's an example, but it can be applied to any quantum application. For example, for quantum computing, the fact that you need 1 billion qubits for reducing the noise. And well, you want to implement a circuit that is simple, but then you are using a quantum logical gate that cannot be implemented in that physical system, and you need to translate that. And suddenly your system needs 40 more qubits, is triple the complexity and depth, and you need 1 billion qubits. And then when you want to execute it, you thought it was going to be fast, but For state preparation, you need 3 hours, let's say. And then you have a queue. And you have 20 more companies that want to execute in the same computer. And in the end, the software and the theory behind is already settled. Everyone knows it. It has been developed. But the quantum hardware is the problem right now.
Can you share your experience, Raúl?
I think Alberto pretty much nailed it. We're seeing like, yeah, from practice, we're doing like lots of, we have a big initiative this year, like on quantum chemistry, molecular simulation. We are building into singularity. Oh, sorry, a tongue twister. Into singularity, what we call singularity materials. And over there, we clearly see the impact, right, on hardware limitations to simulate and select the molecules, big surfaces. The main barrier will be on the qubits.
Do you want to weigh in, Andres, from the hardware perspective or software perspective?
I'm a software guy, so we have a problem if you. Well, one more thing. If we talk about the hardware challenges, we need to talk about what technologies, because it's a race in which participate different companies with different technologies. We have ion trap, neutral atoms, superconducting circuit, and each of these technology has a specific challenges. So from the perspective of the supercomputing circuit, we have clearly two main challenges: the scalability of the chips and the noise. And with the noise, we have the coherence time are very related between there. So these are the main 3 features that we need to understand how can control them. And from the software that I said, we don't know if there are a problem in where quantum computing will be better than the classical solution.
Just to add, how to partition the problems to hybridize. It's unclear. I mean, we will see a growing quantum computers and different ones, as Andres said, ion traps, cold atoms, superconducting qubits. In Repsol, we coined the term quantum solution. That is a combination of an algorithm and a hardware. And we need to explore all of them somehow, and we need to how to partition the problems. I mean, I can have an optimization problem that has integer variables and continuous variables, and I can have a quantum device that it is very good with integer variables, for instance, that are very hard classically, but it is not obvious how to make a decomposition method to really extract all the power of that. So adding what my panelist colleagues has said, I think in the short term that is one issue. And other issue is that, and it is always like for the cybersecurity also, it is compared the quantum adoption to the 2000 effect for in the cybersecurity. I mean, because we have a lot of devices that we need to change, and there will be a huge market. In computing is the same. I said we have a lot of problems formulated, and those are big problems, and we need somehow to understand very well not only how to partition those problems between a quantum advantage and a classical part, because for sure the quantum computer will not do everything. We will have some hybridization, and we need also to understand how to do that translation automatically, because it will be impossible to reformulate all the problems.
Thank you. Oh no, you can wait now. Yeah, turn it on.
Maybe I'm repeating what we has already said because I think it's very like complete answer. But I think like for us also to find the proper use case when it comes to working collaboration with business units, connecting with them, understanding their problem, and trying the problem and understanding the mathematical formalism. And see whether there's an advantage or not, or a potential advantage depending on the technology we consider for the particular use case. I think that's also a very big challenge because you need to gain the trust within the organization, and I think that's very important to collaborate within so things are possible. And I think that all together from the hardware to the software to the business side of things and to have like a good coordination within brings everything together. And this is a very from my perspective it's a key important piece and that must be there.
I wanted to continue the conversation with you, Zenaida, precisely about a similar point, which I think a lot of people will find interesting here, which is thinking about the future of quantum technologies. Will your company require a lot of new staff specialized in quantum technologies? And what kind of profiles will be needed the most, as in hardware, software?
Can you repeat the question?
Yeah, the question will be what profiles.
Okay. Yeah, so actually in this point we think it's good to have a small team at the moment as the technology needs still to develop further. In the future, we don't know. We cannot say the same as when you will expect quantum advantage for optimization problems. You cannot know this thing. And the type of profiles that we typically maybe looking for scientific and programming profiles, maybe physicists, engineers, computer scientists, mathematicians, this type of profiles. Yes.
Okay, I can say a couple of words, at least from our side. I don't want to say everything universal, I mean, but okay, when we came to this journey, it was something like 2019. And the idea about quantum is, will it be? Quantum, will it be? And now that we are coming to an end of the Cuckoo project and we have a team and now people at my company know what a qubit is, the question is not will it be, is when will it be, how and how expensive. So the profiles, many people say we need a lot of talent, and they're probably thinking, or at least I guess, they are thinking about programmers as usual. I mean, for the big companies, software and so on. And I think in the short term, it will be mainly an R&D activity still, at least in the next year. So companies will be exploring somehow and the profiles, and there will be not many in principle because we need to develop confidence in and we need to show really to the managers, say, okay, this is doing this really, and you have the profit. Then it will explode. But we don't know if it does happen, and we are betting for that to happen. So in the short term, very probably there will be some improvement, some increment, but mainly I think, in my opinion, at least from Repsol, will be probably from R&D people.
Yeah, I can share a little. At Multiverse, we don't have like typical profile. We have in the engineering body, I can say, like mostly we have a mix of quantum, also machine learning engineers. If you have like a background in both, it will be like ideal for us. Also, we're recently been hiring like a few optimized operations research engineers, like people that are specialize more into optimization. At the end, we're a software company. Of course, you have to have some coding skills. Our stack is mainly around Python. Sometimes we use low-level coding language such as C, C++, but Python prevails. Front end, we're using, I think, 2 applications, mainly Streamlit to prototype fast, and we have also under our team software engineers. Of course, we have to put things in production, we have to come with all those software best practices. So I wouldn't say like, to conclude, wouldn't say that's like a typical profile. At the end, we always look for growth mindset, right? Someone who would be naturally curious, so we need to grow, learn, and it's fueled by this.
I wanted to ask on that regard, do you think companies should promote internal training on these matters?
Yeah, definitely. We are doing ourselves. We have our main founder, Roman, doing a tensor network course internally. So because we can't find people out there. So.
Do you find these opportunities at GMV, Robert?
Yeah, I would say straight to the point. We founded our own quantum team relatively recently because there are mainly 2 types of projects that are the R&D projects like UCO and Quantum Spain and others that are financed by the government, but by the private sector, you gotta find clients that are interested in implementing or having some kind of quantum algorithm, and you gotta win those tenders. So on that matter, I think currently there's a certain lack of that kind of interest from companies to have their own quantum solutions. So the need for personnel depends on that, because in the end it's all about money. So either you have R&D projects that are financed, or we gotta build this culture of quantum and do dissemination so that companies can have the potential impact that quantum could have in their companies. So they can put projects on the table and you can do them. So yeah, in GMV, it's there are opportunities, but it will all depend in the future. But about the profiles, it's the same. We don't have hardware, so we're more software-oriented quantum algorithm experts, and that kind of profile, the more experienced, more even on the mathematical, physical part, that could understand better more than just data scientist profiles that we have a lot, maybe more specialized ones on quantum.
And Alberto, can I get your thoughts from Dash Photonics?
In Dash Photonics, we have 2 types of profiles, scientific and engineering. I'm going to talk about the scientific one because it's the one that I know and probably the one that the audience is most interested in. In Dash Photonics, we have a research area where we want people that wants to be, well, if it already is, it will be perfect, but usually they are not yet specialists in a field. For example, I'm becoming, as I learn, the specialist in quantum in Dash Photonics, in the research area. But we are interested in people that wants to know more, that doesn't want to be only an expert in one thing, but well, you cannot be an expert in everything, but at least an expert in a field, or let's say like the guy who is going to help the others when there's a problem in that area, and also being knowledgeable in other areas. I'm going to explain, for example, my case. I'm focusing on quantum technologies and quantum computing, but well, in Das Photonics, we are right now we are two persons working on Cuckoo full time, and my companion is focusing on classical AI because when we were researching Cuckoo, we realized that classical AI was very interesting for SIGINT, and he's focusing on classical AI. But he's also working with me with quantum. He's not focusing on quantum. He's not as expert as me, but he knows about it. So if I have a problem, I can ask him, and vice versa when he has problems with AI. And for example, at the same time, for Cuckoo, we don't need photonics, but we are learning about photonic circuits, photonic integrated circuits. And for example, there's another partner, another coworker that is working on photonics, and we usually help him when he needs some help with an algorithm for whatever he needs. So we look for people that wants to be an expert on something, that has interest. For example, we have two co-workers that are doing a doctoral thesis, industrial thesis on photonics and metasurfaces. And we also want people that doesn't want only to focus on one thing, because, well, in academics, there's usually the type of old professor that thinks that its field is the only one, and the others are just taking out his public investment. So that's what we want that for them.
Yeah, thank you. Finally, to wrap things up, I wanted to conclude with a quick question for all of you. We can start with Andres, which is your long-term vision for the future of quantum technology, both for your company and for the industry as a whole.
Well, this is probably the most hard question to answer. From the perspective of my company, of Kilimanjaro, the future will be in principle, if we follow the roadmap that we have, the future will be successful, and the reason of that is because we have a very specific roadmap with an item that contains a lot of details. We know what we want in each step of the roadmap, but we don't know when we solve the challenge. So this is the key of the matter. So if we want to solve in a correct way this challenge, we need to hard work. We need to dedicate all the day, all the night to solve this challenge. And after that, even after that, we don't know if our product will be successful in the market, because at the end, your product is successful only if there are anyone that can pay this. So it's hard to answer. And if it's hard to answer thinking about my company, I can't say anything about all the field. So it's what can I say is will be easy.
First, for my company, I think that quantum computing will be the future for some applications, and of course for defense, because, for example, quantum communications. Once quantum communications are become a reality, SIGINT will be nothing. Since you can't break the encryption of quantum computing, you cannot gather any intelligence. Maybe they will find a way to extract something, well, maybe not extract, but deduce something, but it will become nothing, and the products that my company sell won't be bought because they won't use them. So it makes sense to become from a seller of signal intelligence applications to a quantum communication applications. The same for quantum sensing. We can see that UAVs are going to become the future of war, sadly, because and right now war is not an emerging, but it's an industry that is growing. So it makes sense to invest in technologies that are going to be important for UAVs. And for the industry, in my opinion, I think that's a thought that I think it's interesting. I think there are some parallels to artificial intelligence with quantum computing, because we had for a long time some of the algorithms that right now are mainstream. Maybe not complete ChatGPT, but lots of the algorithms where ChatGPT is based already existed in the 20th century, but we didn't have computers strong, powerful enough to train them. And there were a lot of models that, since we couldn't try them, they were abandoned. It was like, okay, I can't implement this algorithm, store them, keep it. Maybe when we achieve classical computers that are powerful enough, we will try it. And suddenly, before ChatGPT, there were already very powerful AI models, but they weren't popular. No one knew them. And once ChatGPT appeared, it appeared in the media. Suddenly it was that rush. Every company wanted to have its own AI model. Everyone wanted their AI experts. And those who had the AI experts before the explosion were the ones that were first, OpenAI. For example, Google had experts in ChatGPT, and they decided that the model wasn't powerful enough. They believed that they weren't going to be able to achieve a language model with ChatGPT, so they closed that part of the sector of the research. And a couple of years later, OpenAI appeared, and they realized the mistake that they made. So with quantum technology is going to be the same. Some technologies will need, for example, the hardware breakthrough that I talked about before. But it is important to have some experts around, because when that breakthrough happens and when some applications arrives to the media and becomes mainstream, we will see an explosion that probably will resemble the artificial intelligence one that we are seeing right now.
So I can reply partially. So for the company, I would say that the future or a good long-term vision will be a vision where BOA is a quantum-safe bank where cryptography is informed and it's powerful enough to deal with the quantum threat, and also a future where quantum technologies as a whole add capabilities to the existing algorithms, the existing AI, the existing machine learning, because as many people know, it won't substitute what it's already there. It will add capabilities that were not there before. I mean, potentially add capabilities that were not there before. And yeah, that's my comment. And if you want to, well.
So what is long term?
I will say until it's almost fully developed to an already established
What is fully developed? What do we expect?
So in my opinion, I will say adoption for almost any customer.
Almost any customer.
Yep.
Okay, that will happen for sure. Any other comment?
I think I can comment that a little. Anyways, I think first of all, people way smarter than me, like well known worldwide, made failed provisions right before. So whatever I'm gonna say here, don't take this kind of like as true, like, or something you should follow. But the way I see quantum is agnostic, right? It's a disruptive technology, the same way we see others there. At Multiverse, we understand AI as a vertical. itself, similar to an industry. So we see quantum really being a catalyst there, fueling wider and wider adoption. In terms of like adoption by society, it, of course, I think from another question address, we're answering like some industries that have like big bucks, big budgets. They should like, I think, kind of drive this transformation, especially because you're investing, you're at some point in time they're gonna collect the good fruits out of it. I think the main question would be when. I think we kind of like all answered this like somehow here.
Agree. Really, because we learn how to fly. We learn how to cure some disease. We built accelerator particles. We built a lot of things. And what we need to do right now is to build a quantum system that is a many-body system. And we need to cool down to get entangled. We will learn how to do it. And we will learn, in the meantime, something very important about quantum physics, probably. And we will know. And then when we face that, because the mankind is smart, so we will do it. And once we do it, that's why I don't know how will it be also. When and how. Because we are expecting something like a fault-tolerant quantum computer. Okay, wait a second, my friend. We need to realize how to do that. And probably on the road, we can discover something. So that happens. But for sure, I can argue also that we pass, that's my personal opinion. We pass the threshold of the money invested. And that happens also many times. So we have put such a huge amount of money that we will go beyond. And there's another issue, and the issue of strategy for governments. Quantum computing very probably will allow you to know the secrets of the enemy. So there is a highly reason to develop that. So you have the motivation. We will do it. When? How? Details.
All right. In terms of adoption, I strongly agree with Ricardo that it's mostly about expectations. Like, what expectations do we have at the moment or in the media? Because I'm a believer of this Gartner hype curve that most of you might know. 5 years ago in the media, quantum was on the edge and it could possibly solve anything, and this quantum cryptography that would change the world. And now I think we're going downwards about that expectations, as people are seeing that there are also some limitations to quantum technology right now. And as my colleague also said, this also happened with AI. There was a very long AI winter, but the perceptron and even convolutional networks existed in the 60s with these big mainframe machines, but we weren't able to scale it up until the early 2000s or even 2010s. So we're still waiting to see what's the middle point of this. I don't think it will solve everything. I don't think it's also a failure. We're, as we've been saying before, we're trying to figure out what it is useful for, what it is not. We will discard some things. Maybe today quantum machine learning is at the top and there are a lot of publications, and 10 years later, maybe no one cares about it or even regards it. So it's a matter of just finding this middle point. And for my company, I don't know, but I think it will find a place as AI did. For example, in my own company, we only had this software division, but as AI advanced, now we have a full AI division just for AI projects, and I think the same will happen for quantum in a lot of companies. When we find this point, maybe a lot of consulting and other kind of companies will have their own quantum team, but it's not for everything. It's just it will find its place in some use cases.
Great. So thank you sincerely, Robert, Raúl, Zenaida, Alberto, Ricardo, and Andres. Can we get a big round of applause for them? Now I wanted to open up the conversation for the public. So any questions for them?
Well, thank you for the interesting discussion. I want to bring up a point that I think was shortly commented by Raúl. You already talked in general about the profiles that you're looking for, and I wonder, since this quantum field, these kind of applications that you're working on are pretty new, how difficult it is to find people with these profiles when you open up a job position?
Your question was about quantum specifically, or? I would say they're all hard to find. Machine learning, we see more people doing it, but yeah, I'm one example of that. I came to Multiverse as an AI expert from past lives, and quantum was not part of it at all. But now I'm kind of like navigating more comfortably into the other part. They're all hard to find. We're in a big niche market. In terms of quantum profiles, they are also maybe even the physics, and so maybe even more difficult to find. But at the same time, we don't see as much competition for the talent. I still see to some degrees, at least here in Europe, arriving here, like quantum companies kind of like respect each other, like to not like enter into like a talent war or so. But nonetheless, I think we have space for all, right? If you're good, if you're curious, if you maybe don't have it all, we don't require that at all. We just like want to see some specific aspects that you can deliver, technically speaking, and also some big culture fit. There were some. I think there was a comment, and allow me to quote like one of our founders also. We at Multiverse, we decided not to. There are some quantum stars out there. We decided not to hire them because we believed that was not part of our culture. So at the end, it's very hard because we have like very niche profiles. They also have to have like a cultural fit.
Hello, thank you for the session. My question is specifically for Alberto, because you mentioned this thing that I found curious. That it's fine. That you expect that quantum computing is more energy efficient than classical computing once, or you made a comment related to that, right? And I don't expect that, or I don't see how. So you said at some point that between the competition between classical and quantum, like you were discussing, all of you, about which problems, which sector, which kind of application, and at some point you mentioned something like energy efficiency. that right now a lot of energy is spent in classical computing, right? And that if there was a trade-off there, maybe quantum computing could be better in that respect. And yeah, I wanted to know, how do you see that coming?
Well, as my
Friends?
Yeah, let's say friends. Yeah. As my friend said, one of the advantages of quantum computation is the energy saving. And when we compare quantum computing with classical computing, even in the best case scenario, you don't have an amazing advantage that makes you choose between one or the other just for accuracy or efficiency. Because let's say a classical algorithm can solve a problem within a time frame that it's acceptable. And yes, a quantum computer could do it faster, could add parallelization in the calculus, could simplify the algorithm, which could be important for some applications, for example, for satellites, where you have constraints in the weight, the power emission, the energy consumption, etc. But the investment that you have to make to implement quantum computation doesn't appeal companies. For example, is the case of AI. Until AI arrived to the world public, there wasn't a real interest.
Sure. But my point was more that, for example, superconducting qubits work at millikelvin, right? So the cooling bill is huge. So I don't see the energy efficiency being the
right
way.
Now we have, but we don't have, because the quantum computers that we have nowadays aren't the quantum computers that we want. For example, the 1 billion qubits needed for error, it's something that it's awful. You can't really expect to implement anything with that constraint. And for example, the fact that the physical systems force you to use certain gates, certain ways to operate that aren't efficient with the algorithm that you want to implement. So when I say that one of the main advantages that future quantum computers will have against classical ones, and one of the reasons why companies will want to change to quantum computation, I'm speaking, thinking about the quantum computer of the future, one hypothetical computer that doesn't have those drawbacks that the quantum computers that we have now have.
Okay, I guess my point is just that even that theoretical computer that you're talking about will still cost a lot of money and be really, really cold. It's just that the operation that it does cannot be done with a classical computer, but not that both can do it and one of them is cheaper. That's
well, we don't know right now. We don't know what a quantum computer can do. That's one of the problems too. For example, with dash photonics, what we are been doing is implement quantum equivalence to classical algorithms. We are not trying to create our own quantum algorithms without classical implementation. That's, for example, something that until we have a quantum computer without the limitations that we have nowadays, we won't be able to do. Maybe theoretically, using physical principles that could be discovered in the following years, you can think, okay, I have found a new physical law, and with that law, I can guess, or I can propose a quantum algorithm without classical counterpart. But without a quantum computer, I can't try it. And that relationship can be on the other way. I have found a way to create a quantum computer that doesn't have the disadvantages of the ones that we have now. And now I have realized that with this hardware implementation, there are ways to do some calculus that doesn't have classical counterparts. And if you have an algorithm that has quantum advantage and doesn't have classical counterpart, obviously you are going to implement a quantum computer. And if you have an algorithm that can be both implemented in classical and quantum, if you don't have any drawback in the quantum computer, the only advantage would be well, maybe not the only, but one of the main advantages would be the energy savings. And with the with the energy consumption that we have nowadays with classical AI and the limitations that we are going to have in the future with energy consumptions, the fact that almost any industry is consuming more and more energy because their applications are more energy consuming, quantum computation will have that advantage that will help the companies to invest in quantum computation in order to substitute those classical computers.
Yeah, well, yeah, I also have a question that is also maybe somehow related to this one, referring the energy consumption, but also I would like to open it to anyone because I think that all of us agree right now that okay, current devices are noisy. Getting noiseless devices is not only a matter of engineering, but also a matter of being able to do quantum error correction. Because at the end of the day, you won't be able to get a perfectly noiseless qubit. You only want to get a qubit which has a rate of a level of noise which is below the threshold that allows you to do quantum error correction, right? In that case, you have a logical qubit and you can do all of that. So all of these at the end of the day adds a threshold in terms of resources, because you do not only need to have a quantum advantage, but in some applications, but you also need a quantum advantage, including the overhead in doing quantum error correction. And that means that a lot of voices right now in the community are claiming that probably the only real advantages regarding quantum computing compared with classical computing are probably quantum simulation, at least at the moment, are quantum simulation and are the factoring of numbers, because those applications have an exponential advantage, and therefore the threshold in doing quantum error correction won't be an overhead. So my question is whether you're considering this kind of problems, because I feel that a lot of you have talked about the quantum computer of the future, but the quantum computer of the future will have this problem. So are you also including and considering this threshold regarding the quantum machine learning applications, regarding the optimization applications that right now in the community, people are not really sure whether they will work in the fault-tolerant regime? In general, well, I think that if any of you have worked in or have some idea of how all of these applications are going to change, or how they change when you include quantum error correction and you include that overhead, which is probably the main concern right now.
We are not doing quantum error correction. We are at Niskira, so we are exploring this. So we don't know how fault tolerant era will be. We don't know the hardware, we don't know the algorithms even. So the answer to your question is that we are not exploring that at this moment. And that's a problem for the future, probably. But we are seeing, we have some devices, we have a new approach, we have a new paradigm. What can we do with this? And to be honest, we are exploring what to do. And we know that we face a lot of challenges and a lot of problems. But that's the idea of this. And okay, regarding probably also the energy efficiency, we will need to know how the architecture will scale. Because it is true that many qubits need to be cooled down to the millikelvin scale, but they are really small. When you face, yeah, okay. Yeah, okay. But how many transistors do you need? I mean, we need, just to answer your question is, I think it's good to have a critic thinking about things, for sure. Otherwise, we are not doing science or technology. We are doing other things. But probably those problems are problems for the future. When we reach that river, we will cross that bridge. Now we need to know how can we explore this quantum resource, and how can we change our mind, and if that makes sense. I mean, I have not a quantum advantage in my hand, but I am optimistic. Is that all I can say?
Thank you.
Hi, thanks for the conversations. Well, you have already mentioned other lines of activity and projects that you are working on, but regarding the specific Cuckoo project that is coming to an end, are you planning to continue the research and elaborate on the results you obtained and continue your collaborations, or how are you facing specifically the future to continue the results that you got?
Well, I think it depends strongly on the government subsidies program. There's many questions for science. I mean, at least from my side, I can say that otherwise will be very difficult to produce some kind of business model where the risk is lower. Because you need personnel, you need money. I mean, and when you ask for money in a company, they say, okay, when do you get that money back? And if we are doing some research and we get some funding, we can support that. So it is strongly dependent on at least in our case, and how we can get that business model. And nowadays, our strategy is based on getting public funding and participating in R&D programs.
Okay, even at your at the big companies, Repsol and BBVA, because well, I guess that you have innovation departments that you can have. I don't know how big the budget is and how freely you can make it available. But I mean, I see that two different, or maybe three, considering GMV, not two different sizes of companies, Kilimanjaro and Multiverse. I guess that you have a lot of funding right now coming from public funding and. Well, I don't know exactly, but I guess that you already have a lot of financial muscle to keep on working on. And considering BBVA and Repsol, probably, as you were saying, Ricardo, it will depend on public funding, but also on, let's say, internal venture capital for innovation or open innovation. I don't know.
For sure.
And that is a similar position as in GMB and Multiverse and Kilimanjaro, I guess. I don't know.
Quantum guys are not the only ones at home.
Yeah, no, apenas.
We are not the only ones. So there are other researchers, there are other priorities, and they have their own business model. So it is not clear that you can afford only by you. I will be very happy. I will be very happy if that happens, but I cannot assure that. I can tell you that our strategy and our business case at this moment today is based on getting funding.
So let's thank again our panelists for this very interesting session. And thank you all for coming here today.
Yeah, that's all. We have to go out quick because we need to be out at 6, please.
Es muy aburrido. Está como todo el rato así.
Estaba súper bien currado.
Que me mato.
Me alegro un montón, la verdad.
No, pero...